podcast for chapter 3 for electricity for radiation physics for Wenatchee Valley College. This is your instructor Todd Bussey, and today we're going to learn about static electricity. So the first one we have to do is just a little bit of definition for static electricity. So electrostatics is a branch of physics that deals with the force exerted by a static electric field upon a charged object. So an example of this would be you take a balloon, rub it on your hair, and it becomes statically charged, and then you put it up against the wall and it will stay there. So we could figure out the force between the balloon and the wall since they are both slightly charged, and we could see what force is needed to keep the balloon there. So this would be an example of charging by friction. So in this case we have a rubber rod instead of a balloon. So we have a rubber rod and a piece of fur, and we rub them together, and the electrons that can move from the fur go onto the rubber rod, and so the rubber rod becomes charged negatively and the fur becomes charged positively. So depending upon what we rub on what, it depends upon which one becomes positive and which ones becomes negative. On the website there's a table that shows you which ones would become positive and negative. So now we have some laws of electrostatics that we need to look at and understand. One is the repulsion attraction law, and this is like charges repel and unlike charges attract. So in this case for part A, these are two neutral spheres, and so they will not attract or repel each other. But in part B we have two spheres that are charged negatively, so they will repel each other, and two spheres that are charged positively, so they will also repel each other. And in the last case we have one charge that's negative, one charge that's positive, so they will be attracted to each other. So this is the law of electrostatics for repulsion and attraction. The next one is what's called an inverse square law. So this states that the force between two charges is directly proportional to the product of their magnitudes, that's basically how big they are, and inversely proportional to the square of the distances between them. So we will actually have an equation for this. This equation at the right is not for this one, but we will be using this inverse square law variation quite a bit in class when we look at intensities of X-rays and how far they are away. So on the right on the left we have a picture of like a star or a sun or a light, and we have some sort of intensity at some distance away. We move twice as far away, and that becomes 1/4 as bright down here as it was up here because it's twice as far away. So let's do an example with this intensity equation over here. And so this example is we have a light shines on a physics book. Since we're in physics, we might as well use a physics book. With an intensity of 24 candelas, that's 30 centimeters away. You move the light 75 centimeters away because it's too hot, and we want to know what the new intensity is. So let's look at that equation that we just had. And so we have intensity 1, which is our first intensity of 24 candelas. And don't worry about what a candela is right now, it's just how bright something is. And then we want the new intensity, which we'll call intensity 2, is equal to the distance for the new place, d sub 2, squared, over the distance to the original place, d sub 1 squared. So our first intensity was 24 candelas, and the units for candelas are CD, over the intensity that we're trying to find equals, now this is our second distance, so that's 75 centimeters, and we have to square this. And we don't have to worry about putting this in meters as long as we keep the same units. And then our original distance was 30 centimeters away. And now we have to solve for this second intensity. One way to do that is cross-multiplying. So when we cross-multiply, we have 24 candelas times 30 centimeters squared equals our second intensity times 75 centimeters squared. And now to get I sub 2 by itself, we have to divide by the centimeters, the 75 centimeters squared. So we'll have 24 candelas times 30 centimeters squared over 75 centimeters squared. And that will give us our second intensity. And when we put that in on a calculator, we get the second intensity to be 3.84 candelas. So that should make some sense, because since we're moving it farther away, it should not be as bright as it was when we were 30 centimeters away. In this case, it's 3.84 candelas instead of 24 candelas. So that was just a quick example of this inverse square law. Now let's look at the inverse square law for charges. So the person that figured this out was Charles Coulomb. And what he did was he took an apparatus that had this very fine thread attached to a beam that had a sphere on one end and a loop or a sphere on the other end. And then he had another sphere that he could bring close to it. And he did a lot of calculations with a little bit of trig and torque and all of that, and figured out if this moved by 1 degree, he knew how much force was needed to twist this thing 1 degree around. So then what he did was he charged both spheres, like on this right hand side, and brought them a certain distance away, and this bar twisted, and he figured out how far it twisted and figured out the force. He did this with many different charges, like charges, unlike charges, different distances, and he saw a pattern forming. And the pattern that he saw forming brought him to this equation, Coulomb's law equation. So this is a force electric is equal to a constant, and that happens to be Coulomb's constant. We'll talk about the constant in a minute, times the charge of one of the spheres times the charge of the other sphere divided by the distance squared. So let's talk about the Coulomb's constant. It is just a constant, and in this case the value of that constant K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And some books use this as 9 times 10 to the 9th. Either way works fine with me. If you use 8.99 or 9 times 10 to the 9th, it works. The units here basically make it so that whatever we need up here will cancel out, and we'll end up with newtons at the end. So we have Newton meters squared per Coulomb squared. So let's do a problem with this Coulomb's law. The problem we're going to do is we have two small charged spheres that are 15 centimeters apart, and the first sphere has a charge of 2 times 10 to the negative 6 coulombs on it. Coulombs is just a way of measuring charge. The second one has a charge of 4 times 10 to the negative 6 coulombs. And the reason they have pretty small exponents, negative 6 is pretty small, is because a coulomb is a really large unit. And we just want to find the force between those two charges. So that I have more room, we'll just do that on the next slide here. And so let's write down Coulomb's law first. So Coulomb's law says that the force between two charges is equal to Coulomb's constant times the first charge times the second charge divided by the distance between them squared. You'll notice that I put the K up on top of the fraction since it was out front. That just means it's on top of the fraction as well. That just helps with the multiplication a little bit on your calculator. So let's plug in the values that we know. So the force is equal to Coulomb's constant, which we know is 8.99 times 10 to the 9th. And that's units on that are Newton meters squared per Coulomb squared. And we're going to multiply that by the first charge, which was 2.0 times 10 to the negative 6 coulombs, and the second charge, which is 4.0 times 10 to the negative 6 coulombs. And then we're going to divide that by the distance between them, which was 15 centimeters. But you notice we have meters up here, so we have to change the 15 centimeters into meters. If you remember from chapter 1, all we have to do is move the decimal point over twice, and now we'll be in meters, so 0.15 meters, and we have to square that. So we have to put this into our calculator, and remember that when we do exponents, we need to use a special key on the calculator so that the calculator knows that it is in scientific notation. Some calculators have what's called the EE key, which means you push the EE key when you're trying to get the exponent. and other calculators have what's called an EXP key. So you have to look at your calculator and see which one you need to use. So in this case, when I plug that into my calculator, I've got 3.2 newtons for my force. Let's look at the units for a second to see why it's newtons. So we have this coulomb squared on the bottom up here. That will wipe out this coulomb and this coulomb. And we have meters squared up here, which will wipe out this meter squared down here. And so we'll end up with newtons as our answer. And force is measured in newtons. So that makes sense. And it is a fairly strong force because they're pretty close together as far as the 3.2 goes. Okay, let's go on to another law of electrostatics, and that's called the distribution law. And this states basically that the charges reside on the surface of conductors, like a metal, but are evenly distributed throughout non-conductors. So this happens to be a copper wire, and if we could look at the charges, the ones that could freely move would be on the surface of the wire, and there wouldn't be any excess charge on the inside of the wire. So all the excess charge gets put on the surface, and if we had a conductor like rubber is a non-conductor, an insulator, then the negative charges would be evenly distributed throughout the rubber. The next one we have is for the laws of electrostatics is concentration. And the concentration states that the greatest intensity of charge will be on the surface where the curvature is sharpest. So if we look at this left-hand side, this is just a circle, so they're going to be evenly distributed. Even in an oval type thing, they're going to be evenly distributed. But once we get into a sharp point, and that's where the curvature is sharpest, we're going to have an accumulation of charge there that's going to be greater than the accumulation all the other places. So this right-hand side is another example of that. We have a point here, and so the charges will be accumulating at that point. One reason that we have this is Ben Franklin, when he had a bet with a person from England about which type of lightning rod is best. Ben Franklin thought the one with the sharp point, so basically like a spear, would be the best, and the person from England thought one with a ball on the top would be the best. And since we have a charge accumulating at the sharp point of the lightning rod, that attracted the lightning more than the ball did, so Ben Franklin won that bet. And we'll talk about Ben Franklin a bunch of other times when we talk about electricity as well. The next one is law of electrostatics, and that's movement. And this states that only negative charges move along the solid conductors. So it is the electrons, the negative charges, that will move along the surface of the conductor. When we get to current, we're going to talk about the positive charges moving, and that is thanks to Ben Franklin, because he got it wrong when he talked about what charges move. He thought the positive charges would move, but it's actually the negative charge, the negative electrons, that are going to be moving. And that is it for this part of the electrostatics, and we'll go on to some other parts of electricity in the next podcast.